Okay, good morning. Yesterday we talked about finding limits,
My
particularly
apologies. I don't understand.
finding limits numerically, where we were plugging values into a table and examining what happened. Here's another example, very similar to the one we did in class, in video and in class yesterday, where we've got a function f of x, and we want to know what happens as we get closer and closer to an x value of 1. So we create this table, and we plug in numbers into x successively closer to 1. And we do that from both the left-hand side and the right-hand side, numbers smaller than 1 and numbers larger than 1. And we get very, very close, 1,000th away from an x value of 1. And we examine what happens to our function value, our y output. And we could see, as we get closer from this side, it gets closer to a value of 3. And we see the same behavior from this side. And so we say the limit of our function f of x as x approaches 1 is equal to 3. We're predicting what value would fall there. We know from our knowledge of domain that we cannot plug a 1 into this function and get an actual answer. 1 minus 1 gives us the 0 denominator. So we cannot plug 1 into this function. So one way you could think of this is, what would the answer be if we could plug 1 in? And we know that it would, since we're getting closer and closer to 3 from both directions, we're kind of predicting what that value would be, even though it does not actually exist. Okay? We can do this graphically as well. We can look at the picture. We can take your finger, in my case the pointer, and we could trace this graph from this direction. We could see it's getting larger, larger. It hits a value of 2, larger, larger, larger. As we get closer to this x value of 1, our function is getting closer and closer to 3. If we trace the graph from the other direction, it would be coming down this way, we would see that we're also getting closer and closer to a value of 3. A way to think about this is if you put a finger on each side of the graph for the x value we're looking at, we're examining, and traced your fingers together, are your fingers going to come to the same location? Are your fingers going to hit each other? And in this case, our answer would be yes, they are. Well, that brings up the topic about when does this not work? Okay, and there's some other instructions here. Let's go ahead and click to the right and see if it takes us where I want to go. Here we go. Where do limits fail to exist? They give you an example here of the absolute value of x divided by x. If we were to graph this, and we can do that very quickly. How quick it is to utilize this Desmos tool. F of x equals ABS, parenthesis, of x, close the parenthesis, divided by x. And there we go. We've got our absolute value. Now, if we don't do it, an absolute value of x would be that V shape, divided by x, and it changes a little bit. So if we look at this graph, if we were to trace it from the left-hand side, we would constantly be at a value of negative 1. If we trace this graph from the right-hand side, we would constantly be at a value of positive 1. So if you think of it from that perspective, if we were tracing from both sides, would our fingers come to the same location, the same y value? The answer is no. This one would always be at negative 1, and this one would always be at positive 1, and they wouldn't end up hitting each other. The name we utilize for this is something that we call different right and left behavior, or differing behavior. This function at x equals 0 fails to have a limit solution. So we would say the limit of our function as x approaches 0 does not exist. Okay, and there are numerous circumstances in which this could happen. This absolute value is a very, very common example of that. Next one we talk about is something called unbounded behavior. So think about this function, x approaching 0, and our function is 1 over x squared. Well, we know from our our knowledge of domain that we cannot plug 0 into this function. We get 1 over 0, and that does not exist. Let's go ahead and take a look at that graph. 1 divided by x squared. And and I need to square it. Here we go. I'm zooming too much. As we get close to 0 from the left-hand side, what does our graph do? It begins an upward turn, then it increases infinitely. Okay, if you were to plug numbers into this function, if you were to create a table here, and plug in numbers, and we'll go up here, and we want to change this to f of x1. We would plug a number in here close to 0. Let's say we put in 0.1, negative 0.1. We get a value of 100. If we go to negative 0.01, we get a value of 10,000. We were to go one more, negative 0.001, we're up to 1,000,000 already. So what's happening here is this is increasing faster and faster and faster. If we did values from the other side, so we put in 0.1, we again get the 100. 0.01, we get the 10,000. 0.001, get the 1,000,000 again. So from this direction, it's increasing. Now, what confuses students sometimes is that these numbers correspond, 100 and 100, 10,000, 10,000. So it almost seems like whichever one you do, it's going to approach the same number, so there should be an answer. What we call this is unbounded behavior. And if you remember back to your pre-calculus, this is an example of a vertical asymptote. Okay, this is a vertical, an x value that creates a vertical line that your function will not cross. Again, vertical asymptotes are unbounded behavior. They didn't both have to go the same direction. If that had just been 1 over x, one would have went up and one would have went down. In both cases, it's unbounded behavior. We say the limit does not exist. The last one is a little bit less common. We have this function sine of 1 over x. We don't see this a whole lot, but it's good for you to know that it exists. If we were in class, I would take a graphic calculator. Let's see how it looks on here. I've never done it with the Desmos, but we'll try it anyway. One is sine of 1 over x. And there we go. It does look very nice. So as this comes in here, if we zoom in, we start to see more and more and more lines. We call this oscillating. If we keep zooming in, there'll be so many lines that it will just black out our entire screen. Okay? The name for this is called oscillating behavior. What's happening here is as you get closer and closer to that x value of 0, this graph bounces up and down between negative 1 and 1, like a sine function does, faster and faster and faster and faster, so much so that we cannot identify an actual value that it approaches as x equals 0, because as close as we get to 0, it continues to oscillate faster and faster and faster. And we call that oscillating behavior. And that is another example of where a limit does not exist. So you need to be aware of those three topics. So far, we've talked about how to find a limit using numbers, plugging in numbers, and how to find a limit by looking at a graph and just tracing it with our fingers. We'll do some more practice problems on those today for you to submit. And tomorrow, we're going to start talking about how we start to find these solutions algebraically. So thank you for listening. And if you have any questions, don't hesitate to reach out.